Hi, this is Professor Fernandez, and we are doing video 1 here in lesson 26. So this video is about the optimization of transcendental functions, and we're going to be working through two examples from Calculus Simplified. We are doing optimization here, right? We're going to be finding absolute extrema of these functions. So I am going to assume that you've done some work on optimization before. In particular, if you want to review, check out videos 14.1 through 14.2 for a discussion of things like critical numbers, critical points, and extrema in general. All right, I'm going to use that information, so I'll kind of review it as we go here to solve these two examples. Let's take a look at the first one. Find the absolute extrema of this function over this interval. Okay, so first step in the procedure, I should mention that the procedure that I'm alluding to here is box 4.4 in Calculus Simplified, if you have the book or want to take a look at it. Anyway, the first step here is we have to, first step is to verify that we could do this. So this function is continuous and the interval that we're given is closed. That's just one of the suppositions in this box 4.4. And, really it's not a requirement. However, it does make life a little bit easier if you know that the function is continuous and you're working over a closed interval. Okay, so what do I do then next? I find the derivative. So let's find f prime of x here. This function f of x is a product of two functions, x and e to the minus x. So I'm going to use the product rule, which says derivative of the first times the second plus the first times derivative of the second. Okay, differentiating x, power function, power rule, the derivative is 1. Okay, differentiating e to the minus x. So this is a composite function of e and negative x. So I need to use a chain rule. So the derivative is the first, you write over the same function. This is the first step for exponentials when you differentiate. And then you multiply by the derivative of the inside function. So that's negative 1. Okay, so I'm going to simplify things here. I get e to the minus x e to the minus x. I can factor out an e to the minus x, and I get 1 minus x. And if I want to write this as a fraction, right, I can remember that e to the minus x is 1 over e to the x. So there we go. That helps, kind of. You'll see why in a minute. But now we have to ask ourselves, where is this equal to 0, and are there any x values where this does not exist? I always like to start with this first because usually the answers don't, as it is in this case, right? The only thing you might be worried about here is dividing by 0, but the exponential function e to the x is never equal to 0. So there are no points where the derivative, which is what we calculated, this thing, is undefined. Okay, are there points where it's 0? So let's set 1 minus x over e to the x equal to 0. I can safely multiply both sides by e to the x because, again, e to the x is never 0. And so I'm left solving this, which gives me x equals 1. So that is the only critical number, in other words, place where the derivative is either 0 or undefined, specifically, in this case, 0. Okay, I'm just trying to find some space for myself. So x equals 1, so I'll get rid of this and use the bottom space here. Okay, so I have x equals 1. And now what do I do? Well, the next step in my procedure, because I have a closed interval, is I'm going to find the y value at x equals 1. I'm also going to find the y values at the endpoints, right? Those are the critical values. Okay. So f of 1, I'm going back to the function, not the derivative. That's a common point of, easy place to make a mistake, the function up here. So f of 1 is 1 times e to the minus 1. That's 1 over e. F of 0, so I put in a 0 over here. I just get 0 e to the minus 0, so that's 0. And then f of 3, I get 3 times e to the minus 3, so 3 over e cubed. All right, and then I'm just left to figure out which one of these is the absolute maximum and the absolute minimum. So to do that, this is the third step in the procedure. I find the largest of these values and the smallest of these values. All right, so the smallest of them, these two are positive numbers, so the smallest is 0. So I'm going to just give myself a little room here. Oops, that disappeared. So absolute min at x equals 0, and then of f of 0 is 0. Okay, and then what about the maximum? So absolute max at, so then you got to compare these two values, see which one is larger. There are a variety of ways that you could do this, but you could use a calculator or go to Wolfram Alpha or something to just approximate these in decimal expansions. The exponential grows exponentially fast, right? It's the exponential. So you would expect that this number would be smaller than that one, and indeed that's true. So we have an absolute max at x equals 1, and the actual value of that maximum is f of 1 is 1 over e. Okay, so we did it. We found the absolute extrema of this function over this interval. All right, so we're done with that example. All right, let me do then the last one down here and talk a little bit about some other tips and tricks at the end of the video. So the second example here says, find the absolute extrema of g of x equals x minus 2 ln of x squared plus 1. All right. Similar thing, this is a function defined on a closed interval, and at least on this interval, it's a continuous function. And in fact, because we are taking the natural log of x squared plus 1, this thing, its smallest value is 1. So it's never, it doesn't have any negative values, generate negative values, or generate 0. So in fact, the domain of g of x is all real numbers. All right, so this is a pretty nice and well-behaved function, especially on the interval of interest. Okay, so run through our procedure again. Let's find the derivative. So differentiate I get 1, minus 2 times the derivative of ln of x squared plus 1. That is a composite function, so we're going to use the chain rule. You might remember that the derivative, and I talked about this in a previous video, might have been video 20 in lesson 25 or 24. We talked there about how the derivative of ln of a function of x, u of x, is 1 over u of x times the derivative u prime of x. So we're going to use that here. So the derivative of ln of x squared plus 1 is 1 over x squared plus 1 times the derivative of that, which is 2x. Okay, great. So I end up with 1 minus 4x over x squared plus 1. And that is my derivative. Once again, I'm looking for where this derivative is equal to 0 or is undefined. Again, I have no values where it's undefined because the only thing that could go wrong is divided by 0. X squared plus 1, never equal to 0, so no points where the derivative is undefined. So next, let's set this equal to 0, see if we get any critical numbers from there. That yields this equation, which then I can cross multiply here and turn into x squared minus 4x plus 1 equals 0. This is an equation that probably you want to use a quadratic formula for because it does not seem to factor that well, right? The factors of 1 are 1 and 1, and those two do not add up to negative 4. So I'm going to use a quadratic formula here just to save time on this video. If you do that, you end up getting x equals 2 plus or minus square root of 3. Okay, you can run through the quadratic formula and end up with those two outputs. Great. So those are my only two critical numbers in this problem. The next step then is to find the y value at those critical numbers, g of 2 plus and minus square root of 3, and then also find the y value at the endpoints, right? G of 0 and then g of 10. Okay, and I'm going back to the function g, right? G of x here. I'm going to save you some of the work here. I'm going to do the ones that are easy to do. Pretty much the only one that's easy to do is g of 0. So if I substitute 0 in there, I'm left with ln of 1, which is 0, and I have a 0 there, so g of 0 is 0. Everything else is going to generate some decimal number, right? So I'm just going to give you the approximations. So g of 10 ends up being about 0.8, g of 2 minus root 3 about 0.1, and g of 2 plus root 3 about negative 1.7. And then as the last step in my procedure, I'm going to find the smallest and the largest of these four numbers. So scanning these four numbers here, right, the smallest one is this one, negative 1.7. So this is the absolute max. So at x equals 2 plus square root of 3. That's the location of the absolute max. Excuse me. The actual absolute maximum itself is this y value. Sorry, minimum, absolute minimum. Okay, absolute maximum, scanning these four values again, looking for the largest y value. That is over here. Absolute maximum at x equals 10. And then the actual value of that absolute maximum is g of 10, which is about 0.8.